So a quick sort of outline, I won't talk too much on this. Right, real objectives here are how can we power an intelligent gateway to defend devices behind the gateway that the devices themselves weren't designed to work particularly in advance with that gateway. Can we identify IoT-like devices from D3 event data? I'm going to call that NetMon for the rest of my talk. And as a defender, hands up who are cyber defenders. Who likes to keep things secure?
Defending against what?
Okay, any attack. Defend them against attack. Okay. Who's a cyber? Okay, let's go the other way around. Who's a cyber attacker? Usually at a Black Hat conference, all the hands go up. We can break into anything. Keep your hands up if you can guarantee to stop someone getting into a particular thing on the network. All the hands go down. We're great at breaking in. We're very lousy at keeping people out, and that will become a bit obvious later. Can we identify some devices that are easier to defend and some that are harder to defend? The stinkers that I won't even try defending. Can we build up a tool chain to automatically build up some of the D3 statements that Nick has been in his introduction to? I'm not going to look at static expressions or static inference. I'm going to talk a little bit about how we might produce dynamic behaviour descriptions for devices. But we really want to be able to feed these gateways, these IoT gateways, so that they can do a job of doing some defending. I'm very fortunate in my academic pedigree that my PhD grandfather, my academic grandfather, my PhD supervisor's PhD supervisor, was the youngest cryptanalyst at Bletchley Park. His name is Donald Mickey, and Donald used to play chess down the pub on a Friday night with Alan Turing. Now, Alan was interested in what were the limits of mechanised calculation, and his thesis in 1936 shows that his finite little machine accepts an infinite number of programs. Now, one of the things we've learnt in the pandemic is that the vernacular use of the word exponential doesn't map onto the mathematical use of the word exponential, which is a doubling of things every period. How about we struggle with this idea of countably infinite? How many good programs are there from this infinite space of programs, and how many bad programs? Well, there's an infinite number of good ones and an infinite number of bad ones. And it really does depend on the context. Your good ones might be different from your bad ones, from your good ones. So the cyber defenders are up against it. Actually, humanity is up against it, because this man has released Pandora's box. We really don't know what this collection of his machines are going to do and how we're going to control it. So my hypothesis, or my hypotheses here are, hopefully these IoT devices are relatively simple and they should do a limited number of dynamic things. They should be low volatility if you watch what they're doing. And my second hypothesis is that we can use the data that we see on the network to induce descriptions of dynamic behaviours. So as a bit of a tool chain, the first set of slides is about capturing the data and identifying an IoT device. So actually, I've got a monitoring device. This is basically a plug and play, drop it in just behind your router, and it automatically collects data using the common intrusion detection system, Zeek, which effectively eats the PCAP and produces some metadata. That metadata is stored in a really nice relational temporal database, which has a nice schema about it. But the master table, the connection table, includes a few fields and then points into a service-specific table. So, for example, the DNS lookup will appear in the connection table, but the details of that particular lookup will appear in the DNS table underneath, and there's a nice key directly into that. So this is the data that I'm using, and the collection context is a small business where the system was running for 6 months and was capturing the data there. The log files are produced on an hourly basis and pushed off to a local cloud service, AWS, where some of the data manipulation is done. And during the 6 months, we saw between 28 and 185 devices traffic go through the monitoring unit. That doesn't mean they were the only devices there, but depending on where the system is installed, you can only see what flows through that leg of the network. The number of connections a day range up to about 500,000. So that's this orange trace here on the 6 months, day by day, number of connections. And used a volatility measurement based on some mathematics that was also developed at Bletchley Park by Jack Good and Alan Turing, called the simple Good-Turing frequency estimator. And they were interested in the mathematics because they were trying to look at the occurrence of bigrams in German in their cryptography balance business. So what we've got here is we see this sort of weekly cycle of number of connections. This trace here is about the number of calls out and responses back into the network. And these traces here are this volatility prediction for the entire network. And so this is looking at the entire network. Now, can we use this volatility metric to identify IoT-like devices on the network? Remember, we don't know what's going on this network. We don't have a catalogue of the devices there. We just ship this device out, they plug it in. Okay? So we've got really very limited guaranteed intelligence about what devices are there. So how about we rank all of the devices by their average volatility? And that's this top. So there are 185 devices. This is a log scale. So the stinkers are up the end here. If you're going to put your hand up, volunteer to defend one, steer down this end because they are likely to be easier to defend. So the 12 lowest ranked devices expanded here on this bottom line. And what was really sweet was when I did the analysis, I thought, oh, I wonder what each of these devices were. And one of them, this one here, I thought, oh, I think I recognize that IP address. And it turns out to be the monitoring device itself. So now I actually have a device that I can see in the data, and I happen to know how it works. So it's always good when doing a first cut piece of AI is to know the answers.
When you say volatility, does this mean the uncertainty as to what, when, and how much traffic it's going to make, or?
It's a measure of what we didn't see today, which we could see tomorrow. So low volatility basically means everything we saw today, we're likely to see that tomorrow.
Okay, so it consistently does the same kind of traffic daily basis.
Yes.
But if a device does a weekly upgrade cycle, that would be a high volatility event because it doesn't happen every day.
Yes, I'll show.
Okay.
Well, actually, where was it? So these are two different devices. That's their volatility on a log scale. And you can see there's a little bit of a blip in this blue line. That's a good device. In fact, it's the same one I'm going to, which you're talking about. And this is at the other end. So,
sorry, can I just pick up on that question? Because volatility and predictability.
well,
if there's a weekly update, that's a predictable thing, right? And how does that relate to the?
Well, but I don't know that the device, I don't know that that's predictable,
No,
but his data could
it's not
infer it.
predictability, it's volatility. So the devices that have high volatility tend to be users' laptops because they're going
They go
all
boom,
over
boom,
the
boom,
place.
who
And
knows,
you
right,
can't
yeah.
really say whether yesterday they went everywhere they're likely to ever go again tomorrow. They're just going all over the place.
And is your volatility to do with time or destination or both or?
I can dig into that
Okay.
in the lunch break, I think. Otherwise it'll be here for a while. Right. So we've identified a low volatility IoT device. It happens to be the same as our measurement device. So the next stage then is, can we reverse engineer dynamic descriptions of how that device works? So the first thing to do is to throw away the timestamps, even though they were nicely stamped down to milliseconds, and just keep the temporal order. You're just keeping the temporal order. The device itself had about just over 3,000 events in a 24-hour period. And just jam a few things together to make this thing called a token. I'm interested in the source IP address, the destination IP address, the destination port number, the protocol, and the service. So here the device has an address on the network 10.0.0.145. It's doing a UDP DNS lookup to the server inside the network 10.0.0.137. And we hash the string to make a token, a 9-digit token ID, and we feed it into a natty little sequence mining algorithm called Secateur. Secateur was developed in the late 90s by Craig Neville Manning from New Zealand, who went on to run the analytics team at Google for a while. And it produces a hierarchical grammar. Right, so what we started with were a sequence of 3,200 events, D3 events is what we call them, good. And this automatically builds up this sequence grammars and that produces 366 rules. So let me give a bit of a hand wave at this. I can show a demo of this on the laptop afterwards. Basically, every small square in the trace represents an event. Some of the squares, for example, there's about a dozen here with the red background, have been pulled out as a sequence by this tool, Secateur. So the rules underneath and the actual individual events on top. Each event with the same token has the same code. Little square, each rule with the same number, same sequence, it's the same color behind it. So we get this visualization, and we can click and point and search.
So you're looking for sequences of the same, repeating sequences of events.
Well, that's right. It's picking up repeating sequences, and I'm going to look at a particular sequence and see if it can be explained. So to read the chart, the first event was this one, and it sort of scans down like a TV, and the last one is down the bottom of the page. It's for one device, and whether the device is mentioned in the source IP or the destination IP for one day. So we're really drilling into an individual device. So the technique I'm going to use now to try and extract behaviour rules is a machine learning technique called inductive logic programming. And I think the quickest way to give you a taste of this is to show you the simplest example. So logic programming, anyone heard of the language Prolog? Okay, so inductive logic programming is effectively lazy Prolog programming where you get the ILP system to write your code for you. So a deductive logic program, so the panel on the left, we have some rules. The letters are variables, so X is the grandfather of Y, if X is the father of some Z, and Z is the parent of Y. And we have some facts. Henry is the father of Jane, Jane is the parent of Rob, and so on. And the arrow going down the page deduces from that from the upper portion that Henry is the grandfather of John. Now this is perfectly sound, mathematically, logically sound. The things at the bottom of that panel are believable and true for logic. Now what inductive logic programming tries to do is take some partial set of facts that we know about, which is called background, and some specific examples that we would like to explain or produce a general law for, and propose some candidate hypotheses. So what we'd like it to do is to take the examples of the grandfather relationship, Henry and John and Henry and Rob, and the existing background information or partial Prolog program, and spit out automatically a generalized rule. That's what we would like. And actually the field is relatively mature. It's been going since the 1970s, and it has actually been used to make some scientific discoveries. So how are we going to use it here? So we need to feed into the ILP system this sequence data that was stripped out by Secutor. So we started off with this hierarchical grammar produced by Secutor, 366 grammar rules. We have some underlying network metadata. We have all that lovely stuff that was captured by Zeek. And we have some raw, the raw events, the 3232 raw events. So let's see if we can explain Rule 8. Rule 8 is, has a sequence of 4 events recurring. It occurs 18 times in the day, and the first and the last event are the same in the group of 4, and the middle 2 are the same. So this is what we see in the visualization. Let's see if we can make some sense of it using ILP. So the procedure is, generally in inductive logic programming, is specify one or more examples of the type of thing you would like to explain and set it running. The first thing it does is it takes a single example and produces the most specific set of relationships that relate to that example. So this is called the most specific clause or the most specific rule. And for this particular example, it has 55 elements. That's quite a lot for me to get my head around. It's not all there on the page. Now, in machine learning, there are 2 sort of spectrums. One is you can say that, well, I've given you this example, then the generalization is everything is like that. So everything is interesting. Every sequence is interesting. That's the most general thing you can say about that example. The most specific thing you can say is only this example is interesting. And then we have this rather large search space between the most general statement and the most specific statement. and we need to search through that to find a plausible hypothesis that fits just the examples that you want it to fit, and none of the situations that you don't want. So after doing that search through, it comes up with this much shorter, more general rule that says that this sequence is interesting if it starts with a particular UID event B, and B has another event that, so event B we're not particularly interested in, but we're more interested in the following event, which is event C, which is an SSH connection to a particular device. Okay, it's legible, it seems to make sense a bit. It does explain all of the Rule 8s that appeared. Remember, Rule 8 appeared 15 or so times in 18? Good, 18, right. And there were 7 other rules that fired, well, rules that fired 7 times, 193 and 318. And drilling into the patterns 193 and 318, it looked like they were a spurious extension of Rule 8, which gives a total number of firings in the 24-hour period of this particular rule 24, 1 an hour.
Are your sequences individual packets or flows?
Flows.
Flows.
They're individual events, timestamp events.
Okay, and do you know? Do you look what is so C is an SSH connection and B or A was a DNS request for that?
It turns out they were, yes.
Yes.
Yeah.
What was the other one?
Which was?
Well, what A or B was a DNS lookup? What was the other one?
There are actually C, D, and E. I don't know what the last one was. I know what the third one is.
Okay.
So another SSH back to this place. But having had a look at the timestamps of the event, which was not done in this tool, all of these were triggered at 10 past the hour. So this looks to me like a beaconing event back to the master server. Given that I know the software that's in the box, it does at 10 past the hour check for any control commands back at the server. So I'm not entirely surprised to find this rule be something to start with. This is relatively early stages in the work, but what do we do next? This is meant to be, the graphic's meant to be a genie being held in the bottom, trying to keep it in the bottom. So what we could do then is turn the focus to another unexplained pattern or rule from the sequence miner and start to extract explanations for that. There's no labels on the data. This is one of the real challenges with cybersecurity defense is we've got lots of data but we don't have any labels on it, and in fact the class labels, good or bad, to a first approximation, everything's good. So after this analysis, one might be able to put some labels on there, and hopefully then we can use the generated rules for triggering the detection of unexpected behaviours and generating the D3 statements. Where we're going with this next is
if a rogue device has always been doing something bad, then that would be expected, wouldn't it? So kind of just because something is repetitive doesn't mean that it's good.
someone else has to put the labels on. Hopefully the tool chain will make it easy to give them explanations. Go, oh, it's beaconing. Oh, this device should be beaconing. That's bad. Or, oh, it's beaconing. Actually, that's what this device does, but should only beacon at 10 minutes past the hour. Right, so yeah. But there needs to be a human, in my opinion, there needs to be a human.
And we can also look across 100 of these devices do
That's
this, and one does that. That's
Yes.
probably the bad one.
So,
This is where the distinction between instance and type becomes.
Exactly. Yeah.
so really, it's more of a cyber forensics tool, network forensics tool, but it should be able to spit out some D3 that would be useful. What I see is adding more little Lego building blocks to the ILP system that it can draw on to build up these rules, including the next thing I'm going to try is put some beaconing background knowledge in so that it can see whether the rules are related to that. Naturally, I can integrate it with the graphical prototype, and the way it will be used is, I think this little block would be interesting to explain, go through the process, get an explanation that the human is happy with, and then grey that out, move on to the next piece, and try to fully understand what a device does within the data that we see. Hopefully we'll be able to spit out some D3 statements, push them into the device. Yes?
So do you think that your system would be able to, from the basis of this, derive a rule that says not just that SSH connections at 10 after the hour to that specific Amazon hosts are reasonable, but that SSH connections from this network to this Amazon subnet, because they may renumber, are reasonable?
Sure. So basically the system gives you some plausible things to play with, and you interact and say, yeah, I don't like that much, but I think it really needs to include some reference to subnets. And you haven't found me a rule with subnets in it. Go and search again and find me the next best rules that also includes the term subnet. And ultimately, it's going to be up to a human to say, that's the rule I want to play.
Right now with IDS systems, they're completely useless in enterprises because they get a long list of things that didn't match. Nobody has the clue to even just say yes, 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 yes. And so they just go click all, yes. And then you get into the thing that Ian just said, is that if the device manages to get its bad behavior in there, then he gets blessed. Right? There's a joke about a man who goes to the park with his own bench. Do you know this joke? Where he brings a park bench to the park. Right? And he waits for a policeman to walk by. At which point he picks up his park bench and he walks past the policeman. The policeman says, no, you can't take the park bench from the park. He says, no, look, it's mine. Here's my receipt. I bought it down the street. And he does this every day until the policeman gets bored of him. At which point he steals all the park benches. Right?
We call it throwing a rabbit.
Pardon me?
We call it throwing a rabbit.
Throwing a rabbit, yeah.
So I sort of see a process, it's a bit like this, a tool for helping people build D3 statements from data. I don't believe that there's a good automated technology that you should generate defensive rules and just shove them into the devices. It needs to be a human in the loop, and to keep the human in the loop, the machine learning system has to be able to communicate what it's learned and make that editable. It's an software engineering discipline where you get a head start with some code suggested to you, but then you can finalize and really sign it off.
You talked at the beginning about, you've got some devices that are stinkers, right? So some that are kind of predictable and some that aren't predictable.
Yes.
From what you saw on the data, what kind of percentage of the devices were non-stinkers that would be addressable? So it sounds like the stinkers, you're saying that they're too unreliable, they're too erratic to do this.
Let's do a quick guesstimate, shall we? There's 185 devices, just short of 10%. For that particular network, from what we saw in that period. But that wouldn't surprise me, they were.
It's going to be context specific. As Steve said, that was an SME. So you'd assume the low volatility ones, I'm guessing, would be printers.
Yeah, printers.
Go to like manufacturing where there's no mobile phones out of the network, then there's going to be a low net volatility ones. And someone's home, I reckon it's going to be more 50-50, and slowly moving more the non-volatile, because count the number of phones you've got versus TV speakers, smart sensors, etc. Yeah, 50-50 might be a guess. It depends on
So one of the problems on the right hand side of the high volatility stuff is essentially game devices at home, right? Where effectively their personality depends on what game is being played, right? And so it would be lovely if actually could incorporate a personality into the thing, so that, when my kid's playing Terrarium, it does one behavior, and when he plays Minecraft, it's a different behavior. And when the malware runs overnight, okay, on that computer, then I want to know it's neither of those behaviors, okay, but only one behavior at a time is reasonable. So Terrarium plus Minecraft is not an acceptable behavior. Terrarium plus Discord is, because he's chatting at the same time, right? And so there's a bunch of things where that would really be, I think, would be a real benefit, because we have devices that are not general purpose, but they're not single, like they're not just light switches. They change their purpose over time, but they have a palette of things that way.
So the analysis I've done here is on a day-by-day basis, and to collect that sort of stuff, it would have to be maybe 10 minutes
Of
window
yeah.
time.
Yeah.
And I'm not a great fan of using real numbers for thresholds and stuff. It was just a guideline. Did Jack Good and Alan Turing's techniques they used, are they useful here? They're distribution free, they're easy to use statistically. And could I see a difference in behaviour of devices with it? So it's pretty speaking. Whether I use it as a trigger, your volatility's going up, quick, ring the alarm bells, bring down portfolios, I don't know if I do that.
I think whether that's viable at scale depends on how wide scale the data collection is. Because there's a point at which everything that you want to do is statistically inferenceable from a wide enough data set. And where that data set is qualified, and I think you need a bit of this typing as well overlaid, otherwise you can't correlate between, you'll confuse your PlayStation with your printer.
Well, one of the failures in some of the Windows firewall internal stuff, right, was that you do something, it would not work because there was a firewall involved, and then they added at some point, and I'm not a Windows user, so I really don't know how it evolved. They added some heuristics where there would be a pop-up and say, hey, did you want to enable this thing? And you answer like, yes, I really do. Okay, that's why it was failing. And you actually, in some cases, you want to say, I'm having problems, please do some more analysis to figure out what's failing. And then, then I'll get the pop-up faster. But the most important thing is that we now have the likelihood that analysis is for just that activity, because I'm frustrated and I want to say, okay, please record me, and so you can make a good inference.
We have some challenges if we're only looking at the network, which is all I'm looking at here. If you're on the endpoint, then you can do some other cool stuff. In a domestic environment, you don't want to interrogate the user at all.
We don't want to, but what I just said is that sometimes the user wants to say, I'm having trouble.
Or the easiest way for them not to have any trouble is just not to block anything they want to do.
Right, exactly.
So that's how it's set up.
And that's how we got malware. Right?
Well, and we're going to have an infinite number of malware because we have an infinite number of programs.